We are looking at the tool set of problem solving, and in particular we are focusing on the universal law of problem solving. The very fact that it's a universal law which makes it applicable to all kinds of problem. Yeah, so let's have a quick look at what this law says. The law says for every problem that you think you cannot solve, there exists another similar problem much easier that you can solve. Yeah. Now, from the first look of it, it looks a very simple law, very short and a sweet law. But then the very fact that it's a universally applicable makes it very profound. So let's give it a bit more thorough reading, and let's look at it part by part. Yeah, so what the law says is for every problem. So here we are not talking about a particular problem or some set of problem or a few problems or a particular type of problems. We are talking of every problem. For every problem that you think. Yeah, so here the focus is not on what your teacher thinks or what your sibling thinks or what your parents think or what your friends thinks. It's about what you think. For every problem that you think you cannot solve. Yeah, so here we're not talking about a problem which you cannot solve, but we are talking about a problem which you think you cannot solve. For every problem that you think you cannot solve, there exists a similar problem. So there is another similar problem, very similar in nature. We are not talking about a totally different type of problem. We are talking about a very similar problem. For every problem that you think you cannot solve, there exists another similar problem, much easier. Now the similar problem is much easier and you can solve that. You can solve. Yeah, so for every problem that you think you cannot solve, there exists another similar problem, much easier, that you can solve. Okay, so now that makes it, this law gives you a lot of hope. So whenever you get stuck by a difficult problem, if you have internalized this universal law of problem solving, it gives you a lot of hope and optimism. Whenever you get stuck, you revert back to this universal law, and then you look for a similar problem which is much smaller, much easier, that you can solve. And once you're able to find that and able to solve it, that builds your confidence, and which can be which can be applied in solving the difficult problem which you think you could not have solved. Okay, let's look at some examples. A polygon of 1,000 sides has all possible diagonals drawn from a chosen vertex to others. Yeah, so there is a 1,000-sided polygon. First of all, it's a very big. Visualizing a polygon having 1,000 sides is itself a very difficult task. Yeah, so we are choosing a vertex, and we are drawing diagonals to all others, and we need to find how many triangles are formed. uh, it's a You'll agree that it's a difficult problem, because even if you had drawn an eight-sided polygon, if you had drawn all the diagonals, it looks a mishmash of various lines crossing. Yeah, so this is the this is just an eight-sided one. If you had a 1,000-sided polygon, then it would have been unimaginably difficult. So the first thing that comes to your mind is, I can't do it. Yeah, it's a hopeless situation. Yeah, now you have to turn around this hopelessness into hope. Yeah, by saying that let's try it. And whenever you get stuck in this kind of situation wherein you are not able to solve which you think you cannot solve, then you have to apply the universal law of problem solving and find a similar problem which you definitely can solve. Okay, so the reason why this is a complex problem is because we have got 1,000 sides, which makes it very difficult, not just to draw but even to visualize and imagine. Okay, so let's instead of solving it for 1,000 sides, let's see if we can solve it for a much smaller, much but very similar kind of problems. Let's assume that instead of 1,000 sides, you were supposed to find the solution for only a four-sided polygon, which is a quadrilateral. Yeah, in the quadrilateral, you're choosing a vertex. Let's choose this particular vertex, and you're from this vertex, you're trying to you're drawing diagonals to all other vertices. Okay, so in this case, we've chosen this vertex, and we can draw only one diagonal because the others are all sides. You can draw only one diagonal, which is to the opposite vertex. So for a four-sided figure, for a quadrilateral, we can draw one diagonal, and this diagonal splits the quadrilateral into two different triangles. So we know the answer. We have been able to solve the problem for a much similar. We have been able to solve a similar problem, which is much smaller in scale. So for a four-sided quadrilateral, we know that there's one diagonal from a particular vertex that can be drawn to the other vertices, and we have got only two triangles. Now this gives us some confidence. Let's build upon this confidence, and as we have seen in the generic approach to problem solving, we'll make a nice table, a very structured table, in which we'll mention the number of sides, the figure it looks like, the number of diagonals, and the number of triangles. So we know that in case of a four-sided figure, you get a quadrilateral in which you can draw only one diagonal, as we have seen, and that splits the quadrilateral into two different triangles. Now let's build upon it, and let's take a next step into a five-sided figure. Let's look at a five-sided figure. It will look like a pentagon, which is this. And in this pentagon, we are choosing a vertex. Let's choose this particular vertex and draw diagonals to all other vertices. So in this case, you can see that you can draw only two diagonals. You can draw only these two diagonals, and which split this pentagon into three different triangles. You can see this is the first triangle, this is the second triangle, this is the third triangle. So in case of pentagon, you are able to solve it, and you get three triangles. Now this gives you a bit more confidence. Let's build upon it. Let's look at a six-sided figure, which is a hexagon, and the hexagon looks like this. Let's choose this particular vertex and draw diagonals to all other vertices. In this case, as you can see, you can draw three diagonals, and those three diagonals split the entire figure into four different triangles. Yeah, so for the answer for a six-sided figure is four triangles. Now let's look at the next step is to look at the heptagon, which has got seven sides, and let's choose a particular vertex and draw various diagonals. As you can see here, you can draw four diagonals, and which split the figure into five different triangles. Now as you can see, the beauty of this table is that you can see a pattern emerging. As you're increasing the number of sides, you can see that the number of diagonals are increasing by one, and the number of triangles are also increasing by one. In fact, you can come up with a very generic formula that if you have got an n-sided figure, which will be called an anagon. Yeah, it has got n sides. In case of n-sided polygon, the number of diagonals that you can draw from a particular vertex is n minus 3. As you can see, if n is 4, then you get one diagonal. If n is 5, then you get n minus 3, which is two diagonals. So for an n-sided polygon, you'll get n minus 3 diagonals, and the number of triangles that you get is going to be n minus 2. Yeah, so now you've got a very generic formula that for an n-sided polygon, the answer to the question will be n minus 2 triangles. Now let's apply it in our case, which is for 1000 sided polygon, which will be called a kilogon, because 1000 stands for kilo. And the number of diagonals will be n minus 3, which is 1000 minus 3 is 997, and the number of triangles that you get is n minus 2, which is 998. Yeah, so as we can see, by applying the universal law of problem solving, we were able to shift our focus from not being able to solve a problem to finding something which is very similar, much simpler, and easier to solve, which you can solve it. Once you're able to solve it, then it gives you the confidence to move to the next step, take the next higher step, and you keep on doing it till you are able to solve the problem.